out the solubility equation here. So it's calcium and carbonate, which is just CaCO3 solid. The thing about the table is, if you don't know the formula, it's in the table, the appendix. Hopefully at this point you can figure it out. But it's just a 1-to-1 ratio. And when it dissolves in water, it creates calcium ions and carbonate ions in a 1-to-1 ratio. And so that would mean that the KSP expression would be the concentration of calcium ions to the first times carbonate to the first over 1. So to do the solubility, which is X amount dissolves, you have to set up the chart, and the chart will look the same. It's the same format where you're just going to put some solid into water, and pure water would have no calcium or carbonate ions. And so X amount of your solid dissolves, and at equilibrium, you would still want solid. And the X that dissolves creates these ions in a 1-to-1 ratio. So that would be plus X. So at equilibrium, you'll have X and X. So once we have our equilibrium amounts, then we would plug them into the expression. And this number, this value is in our appendix. So again, all the ones that I give you, either I will give you the constant or it'll be one in the appendix. So don't just Google a number, because it might not be the same, because different references, there are definitely different numbers. And so just use the one from our appendix so that we all have the same values. So the KSP is 8.7 times 10 to the negative 9. Equals X times X. This is not a situation where you would worry about our simplification, because that only applies if you have an initial molarity and you're either adding or subtracting a change. So you cannot eliminate these X's. So this is just going to simply be 8.7 times 10 to the negative 9 equals X squared. And so if you take the square root of both sides, then you will get the solubility. So 8.7 exponent 10 to the negative 9 square root 9.3 times 10 to the negative 5. That's my X. X for molar solubility problems is the molar solubility. And so once you get the value, then you put the unit on it, and then you would put the formula. So X is the amount of this compound that dissolves, which is its molar solubility. And so you'll put molarity, capital M, and then CaCO3. And this is called molar solubility because it's the molarity. If you took away the word molar, it would be just solubility, and that would be grams. And so we would have to convert moles to grams, and then that would be the solubility, which you would just multiply by its molar mass to get its solubility. Okay. So our part 2 of this problem is, instead of water, it's dissolved in calcium chloride. So this would be a common ion effect because they both contain the calcium ion. So if you had calcium carbonate and you drop some solid into calcium chloride water, it would already have calcium there. So not as much calcium carbonate could dissolve. We can prove that mathematically. So everything is going to look the same across the top because it's still calcium chloride turning into calcium, or calcium carbonate turning into calcium and carbonate. Okay. And you're still going to try to put some solid, but instead of putting it in water, you're going to put it into calcium chloride water. And so there's already going to be calcium. So how much calcium will there be? Well, if calcium chloride is dissolved, then all of the calcium chloride turns into calcium ions and chloride ions. And it's not you don't divide it into numbers. This is a mol-to-mol ratio. So if you had 1 molar calcium chloride, when it dissolves, you'll get 1 molar calcium and 2 molar chloride, because you'll have twice as many moles of chloride. We don't care about the chloride because that's not a common ion. We only care about the calcium. And so the number that goes here is 1 molar. So there's already going to be 1 molar calcium present. There is no carbonate. The change is still going to be X amount dissolves. This is a different calculation, so it's going to be a different X. And it will create X amount of calcium and X amount of carbonate. And so at equilibrium, you'll have solid, you'll have 1 plus X and X. Okay. For the behavior of chemicals in water, it's always going to be some kind of X change happens. And it depends on the already known behavior. So the smaller this is, the smaller the change is. So if you want to, you can simplify the math. If you do not want to, then you would need to use the quadratic equation. If you want to prove that what I'm saying is correct, do it both ways and compare your x's. If you don't trust that what I'm saying is correct, this is one of the problems that you could do to prove that what I'm saying is actually true, because it'll just give you a quadratic equation that you have to do. Okay. But I'm going to save time and I'm just going to assume that I'm correct. So can we do the simplification of the math? Yes. If your constant has an exponent of -4 or smaller, -9 is a lot smaller, then we can ignore the x that is plus or minus an initial amount. So not the one that's by itself, but the one that is plus or minus an initial amount. You cannot ignore the initial amount, but you can ignore the plus or minus x. And so I'm going to cross this part out. You cannot ignore the whole entire thing, just the plus or minus part. Equals x times 1. I made that math pretty easy, didn't I? So what is the solubility in 1 molar calcium chloride? 8.7 times 10 to the -9 molar calcium carbonate. What happened to the molarity of calcium carbonate when we tried to dissolve it into a solution that had a common ion? It went down. The common ion effect. The initial concentration of one of the ions results in a lower X value. It decreases the solubility because there is already ion there. It doesn't, when it comes to, if you look at this equation here. It's just the presence of any calcium or any carbonate because they're separated from each other. And so if you already have one of those and you have to multiply them together to get this number, then there's not much more of either one of them that you can add to the solution. So the solubility went way down when there was already calcium present. Because what happens when this starts to dissolve, any carbonates that form, there's a lot of calciums around that it will immediately bond to form the ionic bond and become a solid again.